Everyone, welcome back to the channel. Today we'll design a cloud storage system capable of uploading and downloading files, real-time synchronization, file sharing, offline editing, file versioning, and massive scalability. By the end of this video, you will know exactly how Google Drive and Dropbox work behind the scenes. So let's start with the requirements. It looks simple, like if it says like design a file storage synchronization service like Google Drive or Dropbox. It looks easy, but when functional requirements comes in, like users can upload and download files, file synchronization, file sharing, offline editing support, file versioning, and when there are some non-functional requirement also like reliability, availability, scalability, performance, then it makes this question little bit tricky and harder. So first we have to do a capacity planning, which is known as back of the envelope math. So suppose we have 500 million of users and average users upload is around 20 GB data, then this will come around 10 exabytes of data. So that much of storage we need to store this thing every day, and 100 million files are uploaded. Clearly the storing files inside a relational database isn't possible. We will need a distributed object storage. For that you have to make your decision why you choose uh, DynamoDB or whatever document type data or object storage. So whatever you have to explain in the design explanation. Let's understand the architecture. The client first connected to the load balancer. The request goes through the API gateway. Behind the gateway, we have multiple services like authentication, metadata service, upload service, sharing service, sync service, version service. The actual files are stored inside object storage such as Amazon S3 or Google Cloud Storage. Only metadata like file name, owner, permission, size, and stores locations are stored inside the metadata database. So let's design a high level of diagram. So like in the design explanation, we have chosen for S3 for data storage and for DB, obviously we will be going for a DB. We are using DynamoDB because it is a managed service from the AWS. So all the services we are using, if we choose different providers, it can make our solution costly. Let's try to begin a high level design of this one. So first one, what will be happen? There will be a web or mobile app will be there from where this from where it will be able to upload, and after that there will be obviously a load balancer will be there, and after that there will be a API gateway, and after that there will be multiple services, like one will be this one will be service, another one will be authentication service, and then there will be a sharing service, and then there will be a notification API. So like first we will try for auth service, which can be used by OAuth. After that there will be a metadata service where only the metadata will be stored. Then there will be sharing service, and then there will be a notification service. I will explain each and every component line by line. So first, in the metadata service, there will be one DB also, which will be storing all the DB. Uh, for metadata, we can use, I think we can use Postgres, AWS Postgres or Aurora. We'll use Postgres. And after there, we will have one upload service, which will be uploading the things. And then there will be one chunking, which we will chunk the video. After that, there will be dedupe service for duplication check. And then it will be finally the videos will be stored on the S3 object storage. And all these notification will go via Kafka. We will use one async service, will be Kafka. Every notification will be posted here, and then there will be a version name because we need to sync, right? So maybe offline, online. So for that, we will be having one versioning service, which will be syncing with auth also. That I need one block here. So this will be a sync service. We will try to have one line, will like dotted line, and after that, there will be one WebSocket push. And then WebSocket will be storing to means pushing the notifications to the if we are using a local device, local laptop, we can have on the mobile app also, and we can have a browser cache we can store in the browser cache also because if uh, you are not storing somewhere. So similarly, it will be like that. So we will connect all these via this one. And then you can explain box by box also. I will explain you for this video. I was trying to make it and then we will explain it later. Okay. Now I told you that metadata service will store the file name, owner, permissions, size stored inside metadata database. So we have used a Postgres database. We can. So now let's see how uploading works. The client upload a file, okay, from his web and mobile app. The upload service is split into multiple chunks with the help of chunking service. For example, a 500 MB files can be divided into 100 chunks of 5 MB each. These chunks are uploaded in parallel. This provides several benefits: faster upload, resume interrupted uploads, retry only, failed chunks. After successful uploads, the metadata service stores the file information. Okay. Finally, a Kafka event is published so that connected devices know that file has changed. So that's why we have used this async service so that every consumer will access means get this notification. So here is one thing, deduplication. Imagine 1 million users upload the exact same Linux. What should we store it in million times? No, we calculate SHA-256 hash of every uploaded file. If another file has the same hash, we simply increase the reference count. Only the physical copy exists in storage. This saves enormous amount of storage. Now, file synchronization. There is a sync service, right? Suppose you edit a document on your laptop, your phone should automatically receive the updated version. Here, how it works: the upload service publishes a event to the Kafka. The sync service consumes that. Yeah, so sync service will consume the event. It identifies all devices connected to that user's WebSocket. Notification is sent instantly after this one, and from each device downloads its own copy. This is known as delta synchronization. Now, for the offline, for local laptop, or we can say offline mode, users often edit files without internet access. Every device maintains local cache pending operation queue, while offline all edits are stored locally. Once the network returns, pending changes are uploaded. Now comes the interesting problem. What if two devices edit the same document simultaneously? So for that we need conflict resolution. Suppose laptop edits version 5, phone also edits version 5. Now two different versions exist. There are multiple approaches. The simplest is last write wins, but this may lose data. A better approach is version branching. The system creates two versions and asks the user to merge them. Modern cloud storage use similar strategy depend on the file type. Now, file sharing is implemented using access control. So this is sharing service. So every file contains owner, shared users, permission labels such as read, write, comment. When someone accesses a shared link, the sharing service validate permissions before allowing the access. So they are continuously in sync with the auth service. Now, the non-functional requirements to prevent for reliability and scalability. To prevent data loss, every file is replicated across multiple availability zone. The metadata database is started by the user ID. So partitioning will be there by the user ID. All services remain stateless, allowing them to scale horizontally. Kafka decouples service and making synchronization highly scalable. There are some bottlenecks include large uploads solved using chunking, duplicate files solved using deduplication, million of notification solved using Kafka and the WebSockets, and metadata database hotspot solved using the sharding. Sharding we will do here. So every system design has some trade-offs. Chunking improves resumability but increase metadata. Versioning improves recovery but consumes additional storage. Eventual consistency improves scalability but means devices may briefly store stale data. So understanding these trade-offs is what interviewers are looking for. So we have to give that thing in here. That's how you design a production grade cloud storage platform like Google Drive or Dropbox. We covered object storage, metadata service, chunk upload, deduplication, Kafka-based synchronization, versioning, conflict resolution, scalability, reliability. This architecture is commonly discussed in senior software engineering interviews and reflect many of the design principles used by real-world cloud storage systems. If you find this video helpful, don't forget to like, subscribe, and share it. In the next video, we will tackle another popular system design interview question with a complete production-ready architecture.